Okay. Maybe I will let Louis say a couple of words in the beginning, and we can start.
Okay. Yes, so we are very happy to welcome Gerardo Ciepielewski from the philosophy department of UNAM, the National Autonomous University of Mexico, who will present today a talk on superdeterminism. You see the title here of the paper he published together with Elias Ocon and Daniel Sudarsky last year in the British Journal of Philosophy of Science. So I believe that the talk will be following this paper, which is entitled On Superdeterministic Rejections of Setting Independence. I'm very happy to welcome Gerardo, whom I met about 2 months ago during another talk. I didn't know him before. I knew about his work. Gerardo is doing a postdoc, is a philosopher. What else should I tell Gerardo? Did you work on other fields before? I'm sorry, I didn't know. We cannot hear you.
Sorry, can you hear me now?
Yes.
Oh, great. Yes, I have only worked on the philosophy of physics and mainly on issues related to Bell's theorem. So, yeah.
Excellent. Yes, this paper is quite well known. It has been favorably commented on by several people. So I think it is a great chance to have Gerardo here today. It is a very specific topic, but I hope that for a general public, we will be able to convey the most important idea. There will be a room for discussions after Gerardo's talk. Anastasia, you want to say something about the organization, how we do this?
About our timing, Gerardo will have about 1 hour for his talk. After that, we can have some questions about understanding, maybe. After that, I will give word to Louis for his opponent. For his comments, for his criticisms, etc. And after that, we can have the overall discussion.
Okay, that's great.
Yeah, okay, let's start.
Okay, so thank you to Louis for inviting me here. As he mentioned, we just met 2 months ago, and it's really nice to have the opportunity to continue discussing issues related to superdeterminism, and that's why we are here. I'm going to start the time. Also, thank you to all of you for being present. Thank you for Anastasia for organizing this. And I will begin. So, as mentioned, today's presentation is based on a paper that was published last year, and we will follow closely the structure of that paper. Okay, so let me start with a story. Okay, in 1976, so roughly 12 years after Bell's theorem was published, John Clauser, Michael Horn, Abner Shimony, and Bell himself, okay, were discussing issues related to Bell's theorem, and they uncovered that there is a crucial assumption made in the theorem. Okay, this assumption has to do with positing that the system that they will measure, that one measures in one experiment, okay, must be independent of the settings that one uses to make that measurement. Okay, they all agreed that this assumption was both necessary for the theorem and was benign in nature. Okay, they reasoned that any theory that would challenge this assumption, these types of theories would be later known as superdeterministic, would be conspiratorial and would undermine experimental science. Okay. In recent years, this perspective has been challenged by some physicists like Gerard Toft and Tim Palmer, and some philosophers like President Louis Verwoerd. They contend that a superdeterministic theory might not necessarily be conspirational or damaging to experimental science, among many other things. Okay. So who's correct? An obstacle to solving this question has been the lack of a concrete superdeterministic model. That until recently, and this talk will show you the development of such a model. Okay, here's the plan for the talk. We will do a quick overview of Bell's theorem. In my view, a lot of misunderstandings and a lot of discussions come from misunderstandings surrounding Bell's theorem. So it is always a good idea to start presenting how we understand it to avoid confusions. Okay, then we will discuss, characterize, and say a lot of things about this assumption of settings independence. We will focus on the arguments that people used in the past to say that any theory that would deny it would be conspirational, fine-tuned, bad in general. Okay, and then in the last section we will discuss local pilot wave. Okay, so let's start with Bell's theorem. Okay. Let me just give you an overview of what we're trying to present here, okay? The idea is that we want to know what predictions would a particular type of theories would make. The type of theory we have in mind is what is called a local theory, okay? And intuitively, you can think of a local theory as a theory that postulates that what happens over here in the universe cannot be influenced by something that is over there in the other side of the universe. This is a very intuitive idea. It's a very similar idea to Newton's action at a distance, okay? And so the idea is we want to know what consequences can we extract from such a theory, okay? And the first place to start is to characterize this type of theory. Oh, what is a local theory? And here we have Bell stating, trying to capture this idea of a local theory. And I will read. The direct causes and effects of events are nearby, and even the indirect causes and effects are no further away than permitted by the velocity of light. This is the principle of local causality, and this is the attempt by Bell to capture what a local theory would have to say. Okay. Of course, this is this is influenced by special relativity, by positing that the limiting factor must be the speed of light. Okay. Now, Bell thought that this principle is correct, but we need to modify it a little bit to be able to make to do math with it. Okay. So he proposed another version of the same principle. Okay. And here it is. I will again read. A theory will be said to be locally causal if the probabilities attached to values of local bubbles in a spacetime region 1 are unaffected by a specification of values of local bubbles in a space-like separated region 2, when what happens in the backward light cone of region of 1 is already sufficiently specified, for example, by a full specification of local bubbles in a space region 3. So it's easier to see what is being said if one has a diagram. Okay, the idea is that one has to do space-time regions separated. Okay, regions 1 and 2, and the idea is that in a local theory you would expect that the probabilities that you attach to these things that Bell calls bubbles, but we will think of them as variables. So the idea is that the probability that you attach to a variable in region 1 must not change by what happens in region 2 once you have the complete information of a slice of the past light cone of region 1, which is what happens in 3. In an equation, we can have it like this, okay? So what this says is that the probability here is B for bubble. If someone has questions regarding this concept, we can go into them at the end, but you can think of it as a variable that some theory postulates. So the probability that a theory postulates must be conditional on lambda sigma. Lambda sigma is the information that is in 3, must be equal to the probability that you assign to that variable, even if you include information of what happens in region 2, which is the additional term that appears on the right side. Okay. Okay. So now we have a rough idea of what a local theory is and we must specify the kind of experiment we're thinking about in Bell's theorem. So we're going to consider an experiment that involves two particles that are going to be sent to two distant locations, okay? And in each location, there will be a physicist performing experiments with binary results for the particles that they each receive. Again, this is more easily seen. We have a source, okay, that creates a system of two particles. We're going to send one of the particles to Alice. We send the other particle to Bob, and Alice and Bob can perform one of two measurements, okay, and they will obtain one of two results, okay. Some terminology, the lowercase a and b will represent the variables of the settings that Alice and Bob use for the measurement they perform. So the idea is that Alice receives the one of the particles, and she can use two settings in the same measuring device to perform one of two experiments, okay? Capital A and B will represent the outcomes that Alice and Bob obtain, and one of the outcomes will be labeled as +1, the other as less than 1, okay? And importantly, and this will be important for the rest of the discussion, we must be careful with how we understand this lambda that will appear a lot in the presentation. Lambda represents what is known as the complete state of the system measured by Alice and Bob. And what is this? Okay, the idea is that we are imposing. We want to know the consequences of any local theory. Okay, and the idea is that in any theory that describes the experiment we're considering, the theory will say that the physical state is represented by some state. Okay, the idea is, well, the description that theory says, that is our lambda. So for example, if we were considering this experiment in the context of quantum mechanics, we would say that the physical state that Alice and Bob measure is a singlet. Okay? If you have questions about this particular state, we can go into the details later, but that's the idea. We're seeing it's an abstract concept that corresponds to the description that any theory that some theory would have about the physical state that Alice and Bob measure. Okay, now we're going to assume two things basically. As I said before, the idea of locality is captured in the principle of local causality. And from the principle of local causality, one can show that this condition, factorizability, follows. However, the details are very tricky and there are a lot of subtleties. So it is cleaner to present the theorem as just assuming in place of the principle of local causality, this condition, this assumption known as factorizability. And it states that the joint probability of A and B conditional on the settings of Alice and B and the state of lambda must factorize in this way. Okay, this assumption represents what we expect from a local theory. Okay, the second assumption is settings independence. It basically states that the state lambda of our theory must be independent of the way Alice and Bob select the settings. Another way to put it is that it must be in principle possible for Alice and Bob to arrange an experiment in which A and B are selected in a way that is independent of the distribution of the possible values of lambda. Okay. As you can see, here you have a distribution of lambda. Okay, so you want to be as general as possible with Bell's theorem. You want to allow that perhaps each time Alice and Bob perform the experiment, the physical theory that you have describing what is going on, it doesn't assign one state to the system they measure, but perhaps there is a big set of possible values. And instead of one lambda, you have a distribution of lambdas. Okay. Okay, so now we can state Bell's theorem as follows. No? If one assumes factorizability and settings independence, then the expectation value for the product AB over the whole ensemble, I have an expectation value, it will necessarily obey this inequality. Okay? this particular inequality is the CH inequality. There are many types of inequalities that follow from this. All of them are labeled as Bell's theorem. Okay. In words, what is happening is that first we have a term just for the expectation value of the experiment when we select some settings, and later, if we have time, I have some slides showing you how to make the proof. But the details for now are not important. The theorem is like this. Okay, it's very simple in its steps, but it's very complicated when it comes to understanding all the pieces that are present in the theorem. Okay. One point that I would like to make, and that I hope that we will discuss later, is that as I have presented the theorem is not a theorem about quantum mechanics. There is nothing quantum about this. Okay, it's a theorem about local theories. Now, quantum mechanics enters the picture when one considers what the predictions of quantum mechanics are for the relevant experiment. If one selects the settings, some specific settings, what one finds is that instead of the inequality, one should have this. Okay, so instead of this sum being less than or equal to 2, one obtains that the result should be 2 times the square root of 2. The conclusion is that no local theory can reproduce the predictions of quantum mechanics. And the thing is that we have performed these experiments many times in many situations. We will talk a little bit about that later. And the quantum predictions are the correct ones. The conclusion seems to be that nature, in some sense, is non-local. That at least for some systems in the universe, what happens over here can have some influence on what can happen at the other side of the universe, which is a very strange, crazy, and unsettling conclusion, but it seems to be the right conclusion to have about Bell's theorem. Unless one examines the second assumption in the theorem. This is the second part of the talk. And now I want to basically give a characterization of this assumption, and we will say a lot about why people think that this assumption is very benign, it is very basic, and that any theory that would deny it would be unreasonable. Okay, let me state again the assumption. The assumption is that the state that Alice and Bob will measure must be, that the distribution of the states that Alice and Bob will measure will be independent of the settings they use. And the first thing that we must realize is that a similar assumption is present in all experiments one wants to perform. What do I mean? The idea is that in any experimental situation you can imagine, it is necessary that we assume that how we perform the experiment doesn't modify the system we're trying to measure. In particular, we don't want a situation in which the results of the experiment we have is a result of how we conducted the experiment. For example, imagine that we want to test at what temperature water boils. Okay. We measure temperature, we heat the water, and we see that it is roughly around 100 degrees centigrades. No? Centigrados, yeah. Okay. But to reach that conclusion, we must assume that our act of measuring the water doesn't change the nature of water. If you don't assume that, you cannot make the conclusion that water boils roughly around 100 degrees. Okay? And this applies to any experiment you can think of. Clinical trials, experiments in physics, chemistry, all of them involve some assumption of this type. Okay? In the context of a Bell experiment, this assumption seems reasonable because we have conducted many experiments in which we have varied how the settings are selected. So for example, we have used something called random number generators. We have used digits of pi. So imagine you have pi and you have a lot of, this is an irrational number, so you have many digits. Imagine that we select the settings using the millionth digit of pi, we selected basing our decision on whether or not the millionth digit of pi is even or odd. Other ways we have selected them is by using information that comes from distant quasars. This is a paper from the 2018. The idea is, again, you have systems that come to Earth from very, very far away in time, okay? And you use information about the photons to use the settings. We have also performed experiments in which we use inputs from movies, okay? And we have also used inputs from people playing video games in the paper by Abelan and others from 2018. So why is this relevant? If you want to deny settings independence, what you're saying is that all of these methods to select the settings must be somehow correlated with how the system was created by Alice and Bob, with the system that Alice and Bob created. Okay, well, not created, the system that was created for them to measure. Okay. Okay, sorry. Okay. Now, some people have argued that yes, it might seem like a far-fetched idea, but at the end of the day, there is a common past between the source, the moment when the particles were created, and the settings that Alice and Bob select. So in this diagram, you see, again, you have Alice and Bob, and lowercase, remember, are the variables that represent the settings that Alice and Bob choose. And you can see that there is a common cause C that you can always postulate that is there, and that this common cause somehow correlates the system that Alice and Bob measures, correlates this system with how they select the settings, and that the explanation for the violations of Bell's inequalities has its origin in this common cause. Okay. A comment here, because of the experiment where we used the settings based on information that comes from distant quasars, it means that this common cause in some cases must be so back in time to be as far as 7.8 billion years ago. So this is just to show you why people would think that this is a far-fetched idea, okay? So a lot of people have thought that denying settings independence and in particular doing something like superdeterminism would be unreasonable, and they have offered a lot of reasons. We will just see four for now, but we can discuss them later. We can discuss more if you want later, okay? So some people have argued that such a superdeterministic theory, that is a theory that postulates that this common cause explains any correlation that you obtain between Alice and Bob, must be very complicated, and it would be indeed so complex that it would not be practical to use it. Here's a quote by Kronz: a superdeterministic explanation would extend back indefinitely and will eventually include everything in our universe. So we would not be able to make predictions or explain anything because such a theory would have to involve too many systems. That's the idea. Other people have claimed that such a theory would be not only fine-tuned, but it would be hyper fine-tuned. The idea, and I read, is the initial conditions in a superdeterministic theory must take on a very specific set of values that are correlated with the digits of pi or whatever without any further explanation at all. So the idea is that it seems that when you think in of a superdeterministic theory, what you're postulating is the idea that we are selecting from the initial conditions of the universe those conditions in which we guarantee that the state that Alice and Bob measure is correlated with the settings that they will choose. And we further select the settings so that for any experiment we have performed, we eliminate all of those initial conditions that don't get us to that correlation. Okay. The third objection is that such a theory would not have explanatory power. This objection has not been made by critics of superdeterminism. It's more common to see it as a possible objection that some defenders of superdeterminism have pointed out. And here's how Hossetfelder and Palmer presented. superdeterminism relies on an implausible conspiracy of initial conditions that does not actually explain anything. So the idea is that if you require a fine-tuning for this type of theory, then it seems that the theory would not be able to explain anything, because the explanation would be something like, well, the universe started in just precisely these initial conditions that lead to whatever you are observing. And finally, and more importantly, in the discussion I mentioned at the start, it was argued that superdeterminism would undermine empirical science. And here I will read this quote by Shimony. Unless we proceed under the assumption that hidden conspiracies of this sort do not occur, that is, violations of settings independence, we have abandoned in advance the whole enterprise of discovering the laws of nature by experimentation. Again, there is always an assumption like settings independence in any experiment you perform. And if you deny this assumption, it seems that you are abandoning the possibility of obtaining results from experiments. Okay, so the question is, are they right? Okay, and the problem is that without a superdeterministic model, it is not easy to solve this question. Okay, and until recently, there was no physical superdeterministic model. Okay, and that leads to the third part of our talk, local pilot wave. So let me just say a little bit about what we want to do. And the general idea is that we will start from a theory that is non-local and deterministic, okay? And we will modify it to have a theory that is local, continues to be deterministic, but that violates settings independence, and that by violating settings independence, it reproduces the results that we observe in Bell-type experiment. Okay. I don't know how many of you are aware of the existence of the pilot wave theory. This will be a very, very short description of what the theory is. So pilot wave theory is a modification of quantum mechanics that was created as a solution to something called the measurement problem. The measurement problem is a problem that standard quantum mechanics has. It involves the fact that the theory has two dynamical laws and that it is ambiguous on when do you have to use one of the dynamical laws or the other. Okay, so pilot wave theory is, as I said, a modification of standard quantum mechanics. And in pilot wave theory is also known as Pohmian mechanics. So physical systems are described using a wave function, the same wave function that appears in standard quantum mechanics. But in addition, you add a configuration of the position of particles. So this is what is known as a hidden variable theory, because it postulates that in addition to the quantum description that you have more variables that are present. Okay, and in this case, the extra variables are the position of particles involved in the particular system we're considering. Okay. The theory also gives us evolution laws for the wave function. And it also gives us something that is known as the guiding equation. That is an equation that gives us how the particles will evolve in time according to the theory. Okay. The first part is just the wave equation. Nothing changes there. It's just the same as in standard quantum mechanics. And the second is just it tells us the velocity of the particles as they will move in time. They will evolve in time. Okay. Something that I will mention quickly is that it is clear that this theory is non-local. That is, in this theory, something that happens over here can be influenced by something that happens over there. And that can be easily seen in the guiding equation. I don't know if you can see my cursor. I hope so. But you can see that the term in the guiding equation, the velocity of a particle will in general depend on the position of other particles in the universe. So this aspect of non-locality in the case of pilot wave theory is very explicit. The theory says that how one particle behaves will depend on the position of other particles in the universe, no matter how far away they are. Okay. Now, sorry again, I want to show you a trick. We want to construct a local model from the non-local pilot wave. And to do so, we will add at points in space an n-particle pilot wave system. That is, we will imagine the universe, and instead of thinking of the universe as being described by some wave function and the configuration of particles, we will assume that to each physical point in space, you will assign to that point some internal degrees of freedom that are akin to an to a system or to an n-particle pilot wave system. So you will have an internal wave function and an internal configuration of particles inside of each point in space. Okay. And in addition to that, what we want to say is that how this point behaves in time will depend only on aspects that are present in that point and its internal dynamics. Okay, so by construction, we're making something that is as local as can be. It's ultra local. In what sense? In the sense that there is no even interaction between these points. Each point behaves independently completely. Okay. Instead of a wave function, we now have a wave function field. You can imagine it as a wave function for each point in space. And instead of the configuration of particles, we have now a position field. Again, you can think of it as internal configuration of particles for each point in space. You can have an analogous Schrödinger equation for this wave function field and an analogous equation for the position field. Okay, here you have it. And what have we done? Well, we have a model that is ultra local. No? What happens at each point in space is only determined by the internal degrees of freedom of that point and the Schrödinger equation and the guiding equation inside of that point. Okay, it's ultra local. There is no causation, for example, in any meaningful sense here. Okay. Now, if the information in each point in space is different from point to point, our theory is not very interesting. Okay, we have some very grotesque picture of what is going on in the universe. The interesting thing to note is that if we demand something about the initial conditions in the model, everything runs very smoothly. That is, if we assume this condition that is called homogeneity, but let me just state it in words and then we go to the equations. The idea is that suppose that the internal wave functions and the internal configuration of particles inside of each point, somehow they all coincide, okay? And they all agree with what's the value, what is the correct internal wave function, what is the correct configuration of particles, and they that happens. This is basically what is captured in these two equations, which is just that the gradient for time times at t0 will be 0. That is, there is no variation in the wave functions. And again, the gradient is 0 for the configuration of the particles. So all of them agree at some other point. And as a consequence of this, and as a consequence of the loss of the model, we see that we now have that all the points in space suddenly become coordinated, and we get something akin to Leibniz pre-established harmony. Okay. We recover all the predictions of standard pilot wave, and as a consequence, we can violate the inequalities that were present in Bell's theorem. We can be consistent with all the experiments we have performed today to test these types of experiments. Okay. One important question is how do we impose these initial conditions of homogeneity? No? And there are 3 ways that one could do it. One could just say that we assume that the initial conditions of the universe were such that this occurred. Okay, that would be some type of fine-tuning. Secondly, one could argue that we could say that these 2 equations are a new law of our theory, and perhaps that would make it seem less fine-tuned. Okay, but the third way to obtain this homogeneity is dynamically by changing the equations and introducing some terms that will basically, as time moves forward, will eliminate the gradients and will make them converge, converge all the wave functions. That is a very technical point that if we have time and if anyone is interested, we can go to it. But the larger picture is that we can obtain this condition of homogeneity in the model in 3 different ways. And especially there is a way of doing it dynamically, okay? And what can we say about this model? Well, we can go back to the objections we stated in the previous part of the presentation. So people argued that a superdeterministic theory would be too complex and that it would not be able to make predictions or explanations because those explanations would involve the whole universe and it would be really, really hard. But as I have presented to you the theory, it has just 2 equations and it has just some condition on the initial conditions of the universe. One postulation about the conditions, initial conditions of the universe. So it is not too complex, no? Not as complex as people believed. We can make, in fact, the same predictions that pilot wave theory makes. The second point is precisely that we can make this. It has explanatory power. It is not as people thought that all explanations will be in the form that things happen just because there was some correlation. No, no, no. The theory gives you an explanation in a similar way to the explanation that comes from pilot wave theory. The third point is that if you obtain homogeneity dynamically, the model is not fine-tuned. Okay. There is this other issue related to undermining science. This is a very subtle issue and demands a little bit more of our attention. Okay, so in a standard pilot wave theory, lambda corresponds to the wave function of the system that Alice and Bob will measure. And it also contains the configuration of the 2 particles that Alice and Bob measure. Okay, that's lambda according to pilot wave theory. Okay, that theory is non-local because it turns out that how Bob performs his measurement will be relevant for the result of Alice. Okay, and that is something that is not encoded in the wave function that they use, nor in the configuration of the particles that they have. Okay. Now, the change is the following. In local pilot wave theory, lambda involves an internal wave function, that is the wave function that corresponds to some point in space. It also corresponds to the internal configuration of particles. And this point in space has information about what setting Bob will use. And this information is local and accessible to anyone that is in that point. So lambda is correlated with the setting that Bob will use, okay? And that's why settings independence is violated in this case. But notice that this type of violation requires that one is thinking of a situation in which you basically have something akin to entanglement. And you would not expect that this situation appears in other experiments, okay? So that's why settings independence seems to be violated only for a Bell type experiment, but not in general. So science is not undermined in this sense. Okay. Now, perhaps I have given you the impression that I take this model seriously. No, that's not correct. This is just a model that allows us to ask very interesting questions about what is possible, what a superdeterministic theory would entail. And the model has a lot of very ugly aspects. No? First, it requires an absolute rest frame. Okay, you have something akin to Newton's absolute space. Okay, and I'm not thinking here about the what is called a new Newtonian space-time. No. Here, there is an objective fact about the points in space continuing through time, and there is this absolute rest frame that must exist in the model. Additionally, it is okay for a model to postulate entities that you cannot interact with or observe. But in this case, the disconnect between what is the ontology of the theory and what you can know about the world is huge. You can only basically have access to something akin to the question of whether or not this point has matter or not. Okay. But according to the theory, each point has this enormous amount of information about the whole universe. Okay, so there is this enormous disconnect between the ontology and the epistemology, and of course there is a massive enlargement of the ontology. Okay, so this model is not a good model to think that it represents our universe. Okay, but what have we done? Okay, so we have constructed a local model that reproduces all the predictions of quantum mechanics. No? We have shown that this superdeterministic model, okay, is not too complex. It has explanatory power and does not undermine science. Okay, so it is not correct to say that superdeterminism necessarily has these issues. Okay. We have in the model, you can see how a superdeterministic theory can violate Bell's inequalities. So it can be in accordance with experiments we have performed, and how this violation is by a negation of settings independence. Finally, the model allows us to ask a lot of meaningful questions about superdeterminism in general. Okay. Okay, so I began this discussion with regards to the question of the validity of superdeterminism. Although I have not given you an answer to this question, I have introduced to you a model that shows that some of the fears about superdeterminism were not not as well-founded as previously thought. Okay. More importantly, the model enables us to pose new questions that could, in time, lead to a better understanding of nature's violation of Bell's inequality. Thank you. And if there is time, if you're interested, we can go to the proof of the theorem or some additional aspects regarding the ontology of the theory. That's all.
Thank you very much for your talk. It was very interesting. We really appreciate it. Before we start, does anyone have any questions about the talk? So we are on the same page about it.
Okay, good idea.
For us as philosophers, for the interesting question, thank you very much, Gerardo, for your fascinating presentation. Wonderful, well done. Thank you. And my question is concerning your last question. So 4 questions in the last about, yes, finally, how this model can be applied to another areas of nature. Do you see any ways as a methodology, if we apply your model of a superdeterminism to another maybe areas of nature, because to my mind, the nature is obey the laws of probabilistic determinism, and there are a lot of accidentalities or randomness, uncertainty. So your approach is like a shock for us, like a shock, really, because it's super determinism. In the world we live, we have so much, we observe so much randomness, uncertainty, impossibility to foresee the future. So I understand that you apply to quantum mechanics, quantum world, and do you see any ways where your model can be valid?
Yes. So I want to make one clarification, and then I can answer your question completely. Oh, let me start by answering, and then I go to the clarification. So the model applies across all the natural world. So in principle, it applies to any thing that you can think of. Yeah. So the idea is that the determinism that of the model extends to any physical system in the universe. It doesn't matter if it is biological or not, or if you are thinking of a system from chemistry, the idea would be that it is determined. Now, that leads me to the clarification. The model that I have presented it's super deterministic and it is deterministic. Okay, and the problem is that superdeterminism is a very bad name for this type of theory. Okay, a superdeterministic theory, if we want to be really, really strict with how we use our words, let me go back in the slides. Okay, so superdeterministic theory is the idea that one denies this assumption of Bell's theorem, settings independence, by postulating some type of common cause. Okay, and that idea is actually consistent with an indeterministic world. So the term superdeterminism is a misnomer. But you're right in the sense that our model is completely deterministic and is deterministic across all physical systems. I hope I answered your question.
Okay, yeah, thank you very much. Safarkic, you had
Yes. Thank you, Gerard, for your presentation. And I'd like to ask you about your goal. Do you want to save superdeterminism and avoid non-locality? But why?
Okay.
Is it your ontological position? Maybe you want to save this axiom, or maybe it's kind of epistemological condition. And it's one question, and the second question about error of time. I think you didn't say about contradiction with idea of error of time. You say something about rest frame, but I think if we compare with idea of block universe, and we find many any contradiction with many other arrows of time, I think.
Okay, okay, very nice questions. Okay, the first one is about my motivation. Okay, my main motivation with this work is to have a better discussion regarding superdeterminism. I think that a lot of the papers that have been published on this topic have not been very rigorous with how they extract their conclusions. So a lot of times the arguments are something like, well, such a theory seems like it would produce this or that. And the problem is that if you do not have a physical model, it's really hard to answer those types of questions. It is possible, but it's very, very difficult. So the idea of presenting a physical model is to have a place where we can ask those questions and meaningfully, and we can have a clearer answer to those questions. In the end, I do not believe that superdeterminism is reasonable, despite my talk. But my reasons for that are a little bit independent of what I have presented here. In the end, what must be done is to analyze all the, if one wants to be rational about the whole situation, the expectation is that we should compile all the arguments and make them very, very clear of why people think that superdeterminism is right or wrong, and we should use elements like our model or other things other people have said, and we should be able to see in what direction, whether or not superdeterminism is reasonable or not, where should we go. Okay, so my motive is at this point to have a better discussion surrounding superdeterminism. Regarding the second question, something I did not mention is that there is another way besides superdeterminism to deny settings independence. So let's go back to settings independence. The assumption is that, here it is. The assumption is that the state that Alice and Bob measure, okay, the distribution of such a state is independent of the settings of Alice and Bob. And we want to deny this. And there is another way of achieving this, and it's to claim that there are retrocausal influences. That is, in this diagram, that if Alice's decision of selecting setting A might send a signal backwards in time that influences the system that Alice and Bob created, or that was created in this region, and that it is these influences that cause the results of Alice and Bob to be correlated. Okay, so my point is just that, yes, there are assumptions that are made regarding the arrow of time. And in this case, you assume that the arrow of time goes from past to future. And in our model, it's clear that such arrow of time will be incompatible with some forms with some things of from relativity. You have an absolute space. Okay, so there is an objective. There is an objective answer to the question of when, for example, two things happen at the same time. So yes, I don't know if this answers all of your questions.
Okay, thank you.
And we shall leave the rest of the questions to the discussion. From my point of view, I just want to appreciate how much effort you put into constructing a model of something you're not very sure is true. So to contribute to superdeterminism discussion. Okay, so please, I will, could you stop the sharing, please, so I could share, Luis?
Yeah, sure.
Okay, thank you. So here you go, it's just...
Thanks once more, Gerardo, for the nice presentation. So here in our university, we have the habit to, after the presenter's talk, give a, another person a short discussion, maybe asking some or highlighting some different views. This is just to, stimulate a debate. It's not very frequently done in Anglo-Saxon universities, but I remember from our discussion in Mexico that I'm sure you will appreciate this. So I like to defend superdeterminism. Let me say a few words about some ideas I've recently defended in a few papers. So just to make sure that we all are talking about the same thing, in the Bell experiment, essentially what you measure is a certain Bell inequality, and the Bell inequality can be derived when you know and when you measure. That's what's done. One measures joint probabilities, which I've denoted here by P of X and Y given A and B, conditional probability. X and Y are the left and right spins or photon polarizations, and A and B are the left and right angles. So as Gerardo has nicely reminded us of, to derive the Bell inequality, one has to assume statistical independence, or as Gerardo called it, setting independence, or as other people call it, freedom of choice. There are many other names for this stochastic independence condition, which is, as Gerardo has shown, that the probability distribution of the hidden variables, which determine the outcomes on the left and the right side, the set of variables lambda, is independent of the angles A and B, and also of the choice of the angles by Alice and Bob on their respective measurement stations. So this is the key, one of the three or two, if you prefer, assumptions made by Bell to derive his inequality, which is, as I said, this assumption of independence between the lambda and A and B. Superdeterminism, on the other hand, by definition, rejects this equality and supposes that there are correlations between lambda and A and B. And many people see here different kinds of worries, which Gerardo has nicely listed and commented on. For instance, people say, well, this is violating free will because A and B are choices in the head of experimenters, or A and B are chosen by the very many procedures which Gerardo has also listed. For instance, can be determined by random number generators, can be generated by counting photons coming from quasars, 8 billion years old, and so on and so forth. Okay, so how could this on Earth, people say, how could these variables A and B be correlated with particle properties? Lambda are particle properties, so how on Earth could they be dependent on these very many different ways in which I choose A and B? That sounds to many people, to most philosophers of physics, a strange assumption. I disagree, and for several reasons, but one of them, which let me make a little bit of publicity. That's the paper I wrote last year on this topic, aspects of superdeterminism made intuitive in Foundations of Physics. So one reason, yes, one reason is that, well, I will try to explain it by the following graph. How could one explain these correlation between lambda and A and B? Well, the classic understanding, or one of the explanations that one often reads, and which sounds which has some traction according to me, is on the left side. That's what you could call strong superdeterminism. For many superdeterminists, me included, the idea that simply everything is determined is one of the simplest and most appealing ideas you have in the philosophy of physics. It is a very simple idea, and I claim that it is sufficient to solve many problems of the interpretation of quantum mechanics, okay? This needs quite some explanation to come there, but let me give you hopefully some ideas which will allow you to follow my reasoning. According to superdeterminists, or at least a good part of them, we assume that everything is physical, and therefore everything is determined by what you could call a theory of everything, which is a theory describing physical facts starting at the Big Bang, and which involves, let's call it, variables lambda star. Okay, here on the left side of this diagram, you have at the time of the Big Bang a theory which has variables or the degrees of freedom lambda star, a theory which is a very natural idea for physicists to believe in, right? It is believed that such a theory which describes everything starting at the Big Bang is in principle possible. No one has it yet, but it is a very natural idea that such a theory exists. I call this here an ultimate lambda star theory of everything. And well, if everything is determined, if everything has causes, then it is described by the variables of such a TOE. That means that your quantum properties X, Y, but also the potential hidden variables lambda, as well as the hidden, the variables A and B, whether you conceive them of choices in the brain of experimenters or angles in the experiment, they're all determined by these ab initio variables. To me, this seems a simple consequence of the assumption that everything is determined. If everything is determined, if everything has causes, well, they trace back to the Big Bang. Physicists assume that there is a theory which describes the Big Bang. Immediate or almost immediate consequence is that everything is determined by these lambda star. And this explains where the left, well, this correlation between lambda and AB comes from. Simply, the explanation are the common causes lambda star, okay? Lambda could be additional variables, hidden variables, which we do not know yet, which hopefully in future theories will be discovered. And the correlation between these lambda and A and B simply is mediated, is caused by these ab initio unknown variables lambda star. Okay, that's I think a rather well accepted or popular rationale in the superdeterministic community. What I would like to add is a following twist to it, a simple idea which I think could resolve some of the problems. I assume that there is an intermediate step that you, why do I assume this? Well, a theory of everything which literally explains everything, including where, which angle Alice and Bob in their next Bell experiment will choose, of course, is elusive. It does not exist. We will never be able to predict everything starting from parameters at the Big Bang. I think that most people can agree with that our individual actions will not be predictable. But what could happen is that we construct an effective hidden variable theory, which now involves these variables lambda, which we are looking for, which Hossenfeld and a few other people are trying to construct. And, well, the correlation between lambda and AB here can also be explained, again, by the fact that these ab initio hidden variables lambda star are common causes of lambda A and B. According to Reichenbach's explanation, if you have common causes, you have correlation. I do not see why such a effective level hidden variable could not be constructed. We can do very simple math, which I will not do here, to show that what I assume here, the scheme which is plotted here on the right-hand side, is perfectly in agreement with probability theory, could lead to violations of the Bell inequality by violating this setting independence, because we have a correlation which is mediated through lambda star, even if in gray, this more fundamental level, lambda star, is inaccessible to us. So we have, everything is correlated ultimately, as in superdeterminism, but these hidden correlations can most of the time, of course, not be measured, neither calculated. We know very well that, well, assuming superdeterminism, obviously we cannot calculate the correlations between what I'm saying now and the climate or let's say the weather conditions in Mexico, or between, let's say, the radioactive decay in a helium molecule in the sun and my lifting of a bottle here. According to superdeterminism, these are all correlated because they have common causes, which are totally complex, totally unretractable, simply because it's too complex, but they still exist. There are many such systems in which you can, we did some simulations, you have this in simple billiard tables where you can show that everything is correlated, but only under very specific conditions. These correlations are tractable and measurable. Okay, that's what I'm thinking of. I'm almost ready. I would just say that we have here a scheme of reduction of theories. Okay, we have here a level 0 theory, which we cannot access, but which is supposed to exist, level 0, this ab initio theory of everything. Then we have, hopefully, a theory which we can construct. I call this a level 1 theory with effective lambdas. And then we have quantum mechanics, which is level 2. Let me just say that such a scheme of reduction is very classic in physics. You have it, for instance, between thermodynamics, statistical mechanics, and Newtonian mechanics. Thermodynamics, in this analogy, is a level 2 theory. It can be perfectly well explained by statistical thermodynamics, which introduces hidden variables, new variables, which is most of all the partition function z. The partition function z does exactly as in this model presuppose the existence of zillions of properties, positions, momenta of individual particles of classic Newtonian mechanics. But of course, it also is based on the idea that we cannot know all of them, but they exist. And so simply assuming the existence of parameters is a very useful trick in physics, very classic. You also have it, for instance, you can also reduce phenomenological optics, level 2 theory, to Maxwellian electrodynamics, which introduces new variables, the field variables that you may know, the electric field, the magnetic field, and two other variables. In total, you have 4, which also explain this higher level theory. Okay, if you're, I believe that if I have to summarize these ideas, then it would be the following. I believe one can defend superdeterminism simply by saying, well, this is the old idea of determinism, assuming that everything is determined, including our choices. And then almost automatically, I would say, you have this correlation between lambda and A and B. I'm not saying this theory is devoid of perplexities. Yes, there are some perplexities. For instance, how then to explain that we rarely see correlations and we see them in quantum mechanics, right? We would see them, they would explain quantum mechanics. Well, the explanation would be that quantum physics is dealing with fundamental particles, fundamental fields, maybe these ancient correlations tracing back to the Big Bang, still exist in quantum experiments. We can revive, so to say, ancient quantum correlations which stem from the Big Bang, while we do not see them most of the time. On the other hand, we sometimes do see correlations. There are correlations between the movement of the sun and the Earth, between the moon and the Earth, between, for instance, if you throw a stone in a pond, the wave profiles are strongly correlated. So sometimes we do see correlations. Most of the time we do not see it. Okay. I will end here and simply say that superdeterminism, I think I like to defend it because I think it is, you know, a little bit maltreated. I'm very happy that I think that one important message of Gerardo's talk is that some of the objections to it have been shown now to be not really adequate. It is by theory about which I cannot really judge if it can lead to let's call it what I call here an effective theory, because, well, the theory itself, it has perplexities. I would like to understand a little bit better, and I will ask a few questions to Gerardo in a moment. But what is very nice is that it already takes away a few of the criticisms. Next slide is here. Okay, that is actually, I think, all I would like to say. Well, just to give you know, a different view on things. That's it. I will then now leave time to other questions, and then after that, I'd like to ask.
Thank you, Louis. Should I mention something, or should
sure?
we,
Yes.
So, okay, I have a lot of things that I could say, but perhaps let me just start by saying that you're right when you say that in physics it is very common to have these levels of descriptions of the same system, in the sense that, well, you have a system that is described in some way according to thermodynamics, say, and you have a more profound, more fundamental description of the same system according to statistical mechanics. This is some of the most interesting and beautiful things that you can do in physics. The idea that you show how different physical theories are connected, and ultimately how some of them get reduced from something, from their properties they propose to the properties that another more fundamental theory proposes. The worry a little bit that I have by how you've been presenting the stuff is that your lambda star that you present here in a supposed ultimate theory of everything is the lambda that is present in Bell's theorem. Okay, and I don't know if you agree with that or not, but the idea is that
it's lambda which is in Bell's theorem, not lambda star.
No, I think that the idea is that you have a theory that pretends to be, we don't have fundamental theory. Okay, when we have it, if someone discovered it, we will not realize that it is, because we can never know if it is truly the correct one. Okay, we have different models and we have different theories. Okay, and the thing is that we cannot. One thing is to speculate about how the real world is, and another thing is to talk about physical models and their properties. And the point is just that if you think of a model, any model, you can say, well, what if the universe was described fundamentally by this model? What physical state it would assign to this system? Okay, that is the lambda that appears in Bell's theorem. Okay, so I have trouble understanding this distinction that you propose between lambda star and the other lambda, because for example, you put it as if it exists times 0, but my guess is that it will exist. There is a description by this theory at any time, right? Now, assuming there is a sense in which you can talk about the same time. Okay, there will be a lot of you would have to talk about hypersurfaces, Cauchy surfaces, something like that. Okay.
Yes.
But then Bell's theorem just says that, well, take that fundamental description of that theory that you're postulating, that model, take it seriously, okay? And give me the description of that theory in this slice of the past light cones of Alice and Bob, okay? And the theorem says that if you have that fundamental description and you assume settings independence, then you have a set of inequalities. So I don't understand how the effective lambda appears here, because I understand what you're trying to say. You're trying to say, well, look, no. In the kind of theory we have in mind, something like quantum mechanics appears at some later level, and that can happen. That is actually what happens in pilot wave. Okay, in pilot wave, in addition to the wave function, you have the configuration of the particles. And that lambda, that fundamental lambda, is how you would describe a Bell-type experiment. Okay, so in the past light cones of Alice and Bob, you take a slice, a Cauchy surface, and what you have is a particle position, and you have the wave function of that. It gets a little bit tricky because a wave function is not localized in space, but there is a way to deal with it. Okay, and the thing is that the theorem tells you that for all models that you can think of this, if you allow for this condition that the description must be restricted to this space-like, to this slice of the space, if you reduce it to that, then you will have the inequalities. Our model solves that by doing this very strange trick in which information in points in the past light cone of Alice and Bob, these points include in the internal degrees of freedom information about the whole universe. So our model is pretty crazy in the sense that if you think about it, the variables in one point tell you information about the whole rest. It is a lot similar to what happens in Leibniz monadology. Okay, so you have these windowless points that contain information about the whole universe. Okay, and that is why this local description can have information about what Bob will use, even though it is contained locally. So the thing is, and the problem I have a little bit when I hear the thing that I don't understand, and perhaps you can tell me how to solve this, is I don't understand how if, for example, a superdeterministic has something in mind, such as that when Alice and Bob create a system, a singlet, such system, according to the theory they are trying to describe, can only be described by using information about the whole universe, because that is actually what happens in our model.
Except if you have an effective theory, you can. I think that it's the most useful is you think about the analogy with thermodynamics. All these variables of thermodynamics can be used. They're very useful. All the variables, statistical mechanics works too, in parallel. And we still assume that, you have classical mechanics underlying all this, but you cannot use it. It's too complex.
Yeah, but that's why I said that the lambda we are thinking about is the lambda, the fundamental lambda. So we don't care if a theory is not fundamental. We don't care about it.
No, but
Bell's theorem doesn't deal. You care, but you're not understanding how the lambda in the theorem works. If you want to use another lambda and you want to work with that, I think you can do it. But the lambda that appears in Bell's theorem is the fundamental description of the system.
Well,
I think
lambda is usually assumed to be all the properties which determine the particle outcomes, and certainly not what you're saying, all variables describing the Big Bang, because then even Bell would agree that setting independence is invalid. He says so, and I am saying, well, you can still have a lambda, even if it is not part of this total description of the Big Bang, which in an effective theory will be correlated with A and B, which now surely must be interpreted not as the choices in the head of experimenters, but rather as the angles. And this correlation can be explained by this more fundamental theory, which correlates everything to everything, even if you do not know that theory.
Yes, I think perhaps this is a point that we can just identify that we have a disagreement. I think that it is pretty clear that the lambdas that appear in Bell's theorem must be taken as the fundamental description according to some theory
of the whole experiment, of the outcomes. There is like
of the system that Alice and Bob measures. Yes,
yes.
according to some
and
theory.
not you say yourself in your paper that lambda is not everything which describes the Big Bang, because then it's obvious that setting independence does not hold. You say it yourself in your paper.
Yeah, that is actually what but the thing is that that information is contained in our model. That information is present in each point. That's how the model works. That's how it works.
True. But you know, Gerardo, there is a possibility that there are other superdeterministic theories. Those that Gerard Hooft, as you know, he is one of the top-notch physicists of our times, right? He is a Nobel laureate and one of the top-notch.
Yes.
There is also Sabine Hossenfelder, just for the fun of it, for the people who are listening. Sabine Hossenfelder is, I don't know if everyone knows her. She has become, I would say, a phenomenon in physics. She is hugely popular. She's probably she's without any doubt the most popular physicist, theoretical physicist on internet, on YouTube, and so on. Highly recommend every of her talks, by the way. So she has also been she has constructed a toy model, okay? And she's very clear this is not a realistic model. But just to say there are people who are working on different theories than yours. That's what I would like to develop in a question a little bit further on.
Yeah. Perhaps just quickly, I agree. These people, Gerard Toft, Sabine Hotzenfelder, Tim Palmer, they are very smart. You are very smart, okay? But these people have been confused by a lot of things. The most basic confusion that they have been showing for years, at least in the case of Gerard Toft, which is this confusion spanned like 15 years, is confusing superdeterminism with determinism. Okay, this is very smart people, but that doesn't mean that they don't make mistakes. And I would like to just say that there is a difference between creating a physical model in which I tell you how to describe a system and the dynamics of the system, as I did in this presentation. And another game can be played in which I play to create a function for lambda that if it takes as inputs the settings, I can reproduce the inequalities of the Bell's inequalities. If that is the game, if that is a superdeterministic model, then it's trivial, because the set of possible functions that like that is trivially infinite. Okay, so yes, there are people working on superdeterministic models, and a lot of times people say that they have a superdeterministic model. I cannot say that I have seen all of them, but I can say that most of them involve something like what I just said, creating a function of lambda. Okay, I will give you my lambda is going to be described by this function, and this function takes as inputs the settings. That doesn't tell me anything, because in principle the settings are in the future. So what is happening? That is not a physical theory. I'm not describing any physically. I am just giving you a function and playing a mathematical game. So what I'm trying to say is just that I think we should demand a little bit more from these theories in order to claim that there are superdeterministic models.
Well, you know, I find the model that Hooft has been working on very interesting. Of course, I agree that it's unfinished, but he uses, his theory follows exactly the scheme on the right here of my slide. He assumes the existence of ab initio variables. They're fast varying. They are, you know, unknown, but you can integrate them out, just, you know, as what happens in statistical mechanics. You integrate out the variables of the more fundamental but untractable theory, and then you construct a new theory. I think that's a very, you know, interesting way. Yes, it has led to certain preliminary results, and there are people working on it. I hope that will come to an end, but I do not see here any limitation of finding, you know, a theory which can introduce hidden variables lambda, effective hidden variables, which can explain quantum mechanics. Of course, Hooft does this in, you know, a classic reduction scheme, which is he tries to unify quantum mechanics with relativity theory. And typically, if you would do that, then you would need a more fundamental theory. People believe that's a theory that describes the Big Bang or, you know, times briefly afterwards. And I don't see any problem of doing that. So yeah, I think we should simply at this point say that we disagree here. You believe that it's impossible or unreasonable. I disagree.
Oh, it is possible. No, I mean, you can have, there might be a model similar to what we presented.
Let's see.
Let's see. Okay.
Yeah, your model has, I totally agree, the advantage of being analytically tractable. Of course, you know, opponents will say yes, but it has this Leibnizian touch, as you say, that at every point in space, the particles know what happens in the rest. You know, I find it still interesting. Okay, I'm going to be able to judge it further. I would like to ask some questions, but people will say, well, but it does not do the main thing that a superdeterministic theory should do, which is to unify quantum mechanics and relativity theory, right? But you know, on the other hand, no one is even close to getting there. So, okay, I'm not here, you know, saying that what is more interesting than something else. I'm just saying that we should be open-minded and give a chance to other attempts.
Yeah.
Do you want to comment on me or other people?
I agree absolutely with that. We should be completely open to possibilities. I would just say that we should also try to weigh different possibilities and perhaps use our resources smartly. And my intuition, my idea, and I think not my intuition, I think that I have good reasons to believe that that path might not be the best approach. And I agree. Everyone, a lot of people in physics, a lot of people in philosophy of physics are interested in this theory, that fundamental theory that connects quantum mechanics with relativity. And I understand that this is the motivation.
Okay, so
are there people who want to ask questions? Else I will ask some questions to Gerardo. Maybe a chance to other people.
Yeah, maybe let us stop the sharing, and if anyone has any questions, please feel free to ask them.
Dear Louis, dear Gerardo, can I ask you, maybe both of you, what do you think you say about Big Bang and the fact that universe expanding faster than the speed of light? It means non-locally. This fact contradicts with your idea of connection with lambda and A and B. What do you think?
I have not heard that specifically.
No.
Yeah, but perhaps one would have to check the details. I would be surprised if it is postulated that the expansion goes faster than the speed of light. But something that is pertinent to mention is that it is often claimed that special relativity prohibits faster than light speed. That is not actually right. You can have universes that start with particles moving faster than the velocity of light. What can happen is that you have something that moves slower and then goes to the speed of light. So perhaps if before time starts, you have these things moving faster than light, it can be consistent with relativity. Okay?
If there would be things that happen faster than light, if there are particles who would move faster, then Bell's theorem is not valid anymore, because then you would have also backward causation, and then the problem would be solved. So maybe it is something to look deeper into.
Mm-hmm. Okay. But and I'm not sure that this question. It's my worry about draw of Louis. You show lambda as a common cause, yes? Common
Yeah,
cause.
lambda char. Yeah. Yes. Yes. Yes.
But I'm not sure that this picture is connected with real world, because maybe in Newtonian mechanics, okay, but I think there is no only one common cause for any events.
Lambda
I
star
think
is a set of
it's a simple model.
it's a set of variables. Lambda star is not just one variables. It's this. It are all the degrees of freedom which are part of a hypothesized fundamental theory of the Big Bang. And it is a very natural thought to believe that, you know, all our approximate theories which we have now are can be derived from that theory, and that automatically means that our variables can be said to be caused by these ab initio fundamental variables. Okay, that's you can. The strongest model of causation is perfectly in agreement with that idea. To explain this in detail, I would have to give another talk, which at some point I would very much like to do. It's basically the same thing as, for instance, if you look at statistical mechanics and thermodynamics. Given the partition function, the probability of any values of any of the classic thermodynamic functions are determined, right? In other words, there's a correlation between Z and these other variables. So in this sense, it's in perfect agreement with, you know, Reichenbach's idea. Correlation is in agreement with causation, or at least correlation, if you exclude direct contemporaneous causation, well, correlation is then explained, correlation is explained by causation by earlier causes. So I'm pretty sure of that. It's you know, it seems not to be generally acknowledged, but I'm sure of this. And I would like to give a talk on it, how exactly the relation is between causation and this idea of reduction between theories. I think it's a fascinating topic.
Yes, sorry, I cannot read Cyrillic. What is your name? Sorry.
Well, maybe we can go back to my slide.
No. Okay.
My name, Vladislav.
Yes, sure. Yours.
Ah, sorry.
Vladislav, yeah.
Ladislav. Oh,
Vladislav.
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 Okay, Vladislav. So, no, I think you're actually right. No, the idea is that in Newtonian mechanics, you can think of cases where you have two systems. Even though the theory is completely deterministic, you can have systems that are not correlated in any meaningful way. So this is trivially true. No, imagine that you start a universe from the beginning. Okay, at moment zero, you have one particle over here, you have one particle over there, okay, and they are very, very far away. And then Newtonian mechanics commences, the universe starts, they will not be correlated, okay, at the beginning. After they can start hitting each other and stuff, but from the beginning, they are not correlated. So I think that is what was said. And why is this relevant? Because I agree with the intuition. I think that is behind the question is that there seems to be two ideas are getting mixed. The idea that you have determinism and the idea that you have correlation between two systems. And I agree. Superdeterminism is not determinism, and it is a much stronger claim. The claim is that there is this common cause between the settings and the state. And the thing is that these settings, we have used a lot of different ways of choosing it. We have used, I said, photons, a lot of things. And the claim is that they are correlated with whatever system Alice and Bob prepare in the experiment. So another way to say the same thing is that pilot wave theory is a deterministic theory, okay? And in that theory, the system that Alice and Bob measure is completely independent of the settings that they use. And that is a deterministic theory, okay? So determinism is not the issue here. Perhaps
no, that's all true, but you know, determinism can still explain correlation. Okay, it's the most easy and most straightforward way. And what you can also show is it's the only assumption which explains several questions of probability theory. For instance, where does correlation come from? It explains why there are so many Gaussians in the universe. So it's, you know, no one who knows superdeterminism well would be disagreeing with you, Gerard, that supercorrelation is a wider concept than superdeterminism. But okay, determinism gives you a very simple and straightforward explanation where this correlation comes from. Okay,
but there's a simpler explanation. Right, the retrocausal explanation, which I do not endorse, but I think it's simpler. The idea is that if the settings that Alice chooses goes back and influences the system that they created, well, it is not that the universe has these strange correlations at the beginning of the Big Bang. No. The explanation is that Alice and Bob created some generic system, and this system is sensitive to what happens in the future. And the explanation is very simple in that case. No?
Yes. Well, in the end, you know, we all have to choose between philosophical
yes.
Preferences. So sure, that's fine.
Some days ago on the lecture with my students, I say about entropy, and we say that like an analogy. In the beginning, there was a word or logos. Yeah, I say. In the beginning, there was low entropy. And you say in the beginning, there was a common cause.
Yes, yeah? Yes. And
but
if you have few variables, you know, which correlate everything, I think that fits quite nicely. I would have to think about it, but it seems to fit nicely to this idea of low entropy. You know, just a few fundamental fields which interact. And from there, everything springs, everything comes forth. That sounds like a low entropy thing to me.
Okay, but what is the cause of low entropy?
Now we're entering into the deep philosophical questions, which we can only, you know, dream about, I think. You know, there seems to me, you know, a general simplicity in the universe, and that's one other reason why I like to defend superdeterminism, because, you know, it starts from the simplest hypothesis one can have to do science, which is that everything is caused. Everything has nothing happens without a reason, as Leibniz would say, or as Spinoza would say, everything is determined, and derived a beautiful philosophical theory of it, you know.
Do you agree with Spinoza?
Yes, I'm a Spinozist.
Yeah,
until my
I
last
know.
breath. Until my last breath.
And Gerardo, do you like Spinoza?
I really like Spinoza. Yeah.
May I ask some questions?
Could I have a go, because I think it turned to the discussion turned somewhere where it approached the question I wanted to ask, and I really liked the question by Elena Nikolaevna earlier about how this superdeterministic model fits the uncertainty of our world. And I remember that in your Gerardo, in your presentation, you talked about some ugliness of this model, and one of your points was that it massively enlarges the ontology. So what is your stance on it? What's your position? Okay, could you elaborate on
my position regarding the model, or my position regarding the idea that we should not enlarge the ontology of a model?
If you want to, you can do both.
Or both. Oh, the first one is pretty simple. Look, the model is it's ugly, and I don't think that one should consider it seriously. But the beauty of it comes from the fact that you can have meaningful discussions about features of superdeterminism. So let me give you one example. So one feature that our model has is this idea that somehow, if you look at the fundamental description of the universe according to the model, everything is correlated with everything once you have homogeneity, okay? And one natural question is, well, is this a feature of any superdeterministic model? Okay, and there is a recent paper that I have just skimmed over, but it seems to suggest that this is a feature that needs to be present. Okay, the article, I'm just, perhaps I am misrepresenting it because, as I said, I have just skimmed over it. It is on my reading list. Where is it? Where is it? One second. Okay. Okay. Perhaps I can, if someone is interested, I can send it to you via email. You
Wrote it?
Sorry?
Who wrote it? Who is the author?
It's three authors. It's this Hindu person. Let me check. I know that he has been interested in some of the features of the models that Hossenfelder and Palmer have discussed. I can find it easily if you give me 1 minute. Okay. Okay, the paper is by Carlos Vieira, Ravishankar Ramathan, y Adán Cabello. And the name is Test of the Physical Significance of Bell's Non-Locality. I can send the link in the chat.
Thank you.
I'm interested because that's a natural question that one can have about our model and about superdeterminism in general, and that result seems to suggest that this is a generic thing that you would require in order to have violations for any experiment that you want to conduct. Okay, and other questions you can ask a lot of interesting questions from the model. As Louis mentioned, the model also shows that some of the worries that people had are incorrect. So yes, it has this ugliness, but it doesn't matter in the end because it serves its purpose. And about the virtue of not increasing ontology, I do not have strong intuitions on that. I just think that it is as much as possible, we should look for theories that do not posit much more ontology. But I do not know how this virtue should be weighed against other criteria. Clearly, it goes below empirical empirical information of the theory. Okay, but besides that, I don't know how to weigh it.
Okay, thank you very much. I have another question, but I haven't formulated it yet, so it should wait until that moment.
Gerardo, could you please go to page 25 or slide 25 when you present the model? So you show that, or you claim in the paper that a special choice of the initial conditions transforms your local model into the non-local Bohm theory. Could you guide me a little bit through the equations to show how that works mathematically? So you have the equations of your non-local, of your local Bohm-like theory, and then you say by a very special correlated choice between the initial conditions, you transform this into the. If you could show it on your slides.
Oh yes, let me share the screen. I will share Sotero. Here's Sotero. Which slide is the
I think it's 26.
26? Okay. Oh, it must be
This one. This
26. This one. Okay.
no,
So
one before. No, one before. One before.
okay.
Simply the one where you have the equations of your.
Oh, you have here
No.
a standard pilot
Yeah.
boundary mechanics. Okay. No, in this case, you only have a wave function, the ordinary wave function, and you have some configuration of particles. Okay. This is the standard wave function, the standard Schrödinger equation. Sorry, and this is the so-called guiding.
What's the difference? What's the big yk in the second equation on the left side? There is a big yk and a small
yk. Perhaps this is confusing if you have not seen it presented like this. You have so in Boolean mechanics you have the wave function and you have the configuration of particles. And one way to present it is that to say that, well, you have for particle 1 it is located this, for particle 2 it is located over there, and one way to encode all of this information is by using just one point in configuration space, which is what you have over here.
Okay.
So this is just one way to write all of this information in terms of this unique point in configuration space. So you're saying the velocity of this point is given by this, and from this you can reconstruct the configuration of all the particles. Okay. So this is all in Boolean mechanics.
Yes.
Okay, this is standard Boolean mechanics. This is something that you can do. Perhaps this is confusing. Perhaps I should have mentioned it.
Yeah. I just want to be sure. But my question is, if you now go to your model on the next one slide.
The idea is we will change this model and we will make it ultra.
This slide here. You say if now you choose a very particular set of initial conditions, then you can transform these equations to the one you just showed. Could you show it in a little bit more detail? I don't immediately see it.
Let me. Perhaps there's the confusion. At this point, I have not stated the initial conditions, right? At this point, I only have said that you have instead of a wave function, you have now a wave function field. That is, you have a wave function for the different points in space, okay? And you have, instead of this configuration of particles, you have a position field, which assigns a configuration of particles to each point in space, okay? So that is what is happening. And you can use this wave function, this modified Schrödinger equation, but what you actually are doing is basically assigning a Schrödinger equation to the internal dynamics of each point in space, okay? And the same for the guiding equation, okay? At this point, there is no if you can think about it, you have a very strange theory in which each point behaves, has like this internal Boolean system, and it behaves independently of what happens in other places. Independently in the sense that there's no interaction. What happens in this point is described only by this point. Let me see if I created a slide on this. This is something
that's clear to me, but I don't see how by making your special choice of the initial
how do you get the coordination? Okay.
Yeah, you get back to you transform these equations into Bohm's equations, right?
Yeah.
How does it?
Well, no. These are Bohm's equations. Basically, you have the Schrödinger equation. Sorry, you have the Schrödinger equation, and you have the guiding equation for this wave function field and the position field. And the thing is that now what you need is to say that the internal degrees of freedom, let's say at time 0, are the same for each point. So you want to say that the value for the wave function and the value for the configuration of particles internal to each point are the same.
Yes.
And because of the characteristics of the Schrödinger equation, okay, this This is based on the work of Valentini and others that show you how you will maintain the norm and the properties that follow from the Schrödinger equation and the guiding equation. It ensures that the description that each point gives of the universe is the same. Okay, so in a sense, you have, by construction, you said everything that happens in this point, it's given only by the internal degrees of freedom. And then you add, if we assume that the initial description in each point was the same, then we can guarantee that the description is coordinated in all of the points. Okay, so this is just a trick that you can do to
so you cannot
okay?
use this result by Valentini to say, okay, if we make this Leibnizian assumption, then we transform these equations. Is it really, you know, a mathematical transformation, or is it just, you know, some kind of an obvious thing using this result by Valentini?
Perhaps, are you referring to this point that I mentioned after, that you can have this dynamically?
No. I'm just to understand. You say somewhere, I think almost literally in your paper, that by a special choice of the initial conditions, we can reduce our model, which is local, to the non-local. I would like to understand it better mathematically. I don't.
Mathematically, I don't know if. Okay, so the idea is, how do you move from one to the other?
Right.
The idea would be that this Schrödinger equation and the dynamics that is given by the guiding equation, it's telling you how this field and the position field behave, right?
Mm-hmm.
And from this equation, it's you can see that the dynamics of each point is given precisely by this is telling you that each point behaves according to the Schrödinger equation, right? And if that is the case, if you limit yourself to one point, okay, you will obtain the original Schrödinger equation and the guiding equation that you have in Boltzmann mechanics. Okay. Now the problem is that if you start with a different description in a T0 for different points, this the solutions that you get will in general be different. So you will have a universe in which each point is not coordinated with others. So if you impose that at T0, each point starts with the same internal degrees of freedom, what you have is that basically that you will have for each point the same solution. You will have the same description in terms of information that pilot wave theory gives you. Okay. That condition that you must demand is this idea, no? that the gradients of the wave function as for T0 is equal to 0, which is basically to say that
it's not really sufficient, this condition here. Then not only need the gradient needs to be different, but they need to be, the values also need to be exactly the same, no?
Well, that's how I interpret this equation. It is saying that the gradient of the wave function at T0 is 0 in the sense that there is no difference between the wave function that is described. And the same for the configuration of the particles. Now, there is a very subtle and difficult point that is here, and that would need to be, I would need a lot more of time and perhaps a little bit more preparation, but it has to do with how to obtain this condition for dynamically. And
okay, yeah, that's interesting, but I believe you. I believe you.
Because the thing is that you would have to modify the dynamical equations, so you will have some term extra here, and you have basically some like heat-like wave equation, and you want this heat wave equation to, as it moves in time, to make the gradient of phi and gradient of the position field to go to 0. So
that's interesting. That's interesting. It's cool. But okay, I'm not an expert in Bohmian mechanics, but you know, if I understand Bohmian mechanics correctly, to use it, for instance, in the way that you know, there is a famous Canadian physicist, Steinberg, who did a few years ago a very, intriguing thing. He used Bohmian, or he measured the trajectories of electrons in a double slit, and the trajectories followed basically Bohmian trajectories. Maybe you know this you can apply Bohmian mechanics to a double slit. This has been done 30-40 years ago by a Greek gentleman whose name I forgot, and you get nice trajectories for individual particles. So the average of this behavior leads you to the double slit interference, which quantum mechanics predicts, but Bohmian mechanics, as you have recalled, gives you predictions for individual particle trajectories. And
yes, that is completely right.
yeah.
I don't know the details of the history. Okay, I don't know who did it first. Perhaps it is as you said, but that's correct. In Bohmian mechanics, you can calculate. You can see what happens to the particle all the time. Okay, and the theory is completely deterministic.
Right, Gerardo, but to do this, to calculate these individual trajectories according to this guidance equation that you
yes.
You need a wave function, right? You need to know the wave function.
Oh, of course, you need the wave function. The wave function serves as imagine it is like a fluid that is moving the particles.
Right.
Perhaps
right.
Can you see my screen? Here is a very nice book by Travis Norton, and he has very good diagrams of how the Bohmian particles would move.
Yes, I think that's exactly the figure I was talking about.
Yes.
Yeah, it's very famous. Yes. So now here's my question, Gerardo.
Yes.
I know how to calculate the wave function in particular cases. For instance, coming from semiconductor physics, I know how to calculate it in a semiconductor material and in some other, you simply use the equation and you assume some shape of your potential V, which we can see here. And then you can calculate, for instance, some simple sinuses, and those are the wave functions or the wave function. How do you conceive of the wave function of the universe? Because here, basically, psi is the wave function of the universe, correct?
Yes.
Do you believe that's
can you repeat the question? Just the question. So
yeah,
here, the phi is the wave function of the.
By the wave function of the universe?
Yes. So you, in the more general description, you have the wave wave function field. Okay. So the theory says that in reality you have this object that is composed of the internal wave functions of each point, right?
In your theory.
In my theory, yes.
Yeah.
In pilot wave, you think of it as the universal wave function. Yes.
That's according to how I understand quantum mechanics, a very controversial topic. This is not at all, directly related to your work. Okay, I see what you are doing, I think, but just between you and me and our spectators here, this idea of universal wave function, I fear I'm far from convinced by it.
Why is that?
Because I understand quantum mechanics the way Niels Bohr proposed it, which is that a wave function is basically generated by an experimental setup. I'm a big fan of that idea. Yes, you can ascribe a wave function to a concrete quantum experiment, for instance, the Bell experiment. But to the universe, that's, I fear, a stretch.
Yeah, I think that you should be, you're right in being suspicious of something like that. And I'm also suspicious of the idea that you can do something like that. But think of it this way. The question is how is the universe according to a theory that you're taking seriously? So you're not acting like Bohr and saying that quantum mechanics is somehow a theory that involves the interaction between observers and systems that is has its properties and
Well,
stuff.
yeah,
No, you're
think that's
assuming
correct.
that it's fundamental.
Yes.
And if you do something like that, then the consequence is that there is something like the wave function of the universe. But you should be. There are a lot of things that you should be cautious when you say something like that. It's strange, the idea that you can have the same type of description for an experiment that you conduct in very particular situations inside a lab, and then you can extrapolate that the kind of description to the universe. It seems odd. But
Are you favorable for this idea of the wave function of the universe?
Let me see. I like realistic theories of what is happening in physics. So I like theories that are very clear on what exists, and that is my demand. No? In the case of quantum mechanics, it's clear that there will be something like the wave function of the universe, and that's the proposal, right?
But Bohm
himself
conceive of the wave function in this way? Did he say that somewhere, that psi is the wave function of the universe?
Who? Bohm or
Bohm.
de Broglie? I am not sure, but I am not an expert on.
Anyway, maybe this leads us too far. My next, and that's the only further main question I have, is that, so we see here ideas of the great Leibniz in your model, because yes, the main idea is that there is a pre-established harmony, which makes that in all points of the universe, the information of the movement of all particles of the universe is included, right?
Yes.
Okay. Well, you know, this is in a way, you know, I think a very similar assumption as, you know, my preferred view of superdeterminism, which is that, yes, at the beginning of the universe, there is this total knowledge, you know, which is embedded in this theory of everything, of literally everything. And that means that you can say, well, then you know, in every point of the universe, everything is correlated and everything is known. I think, well, there is a resonance with, you know, classic superdeterministic ideas and this Leibnizian idea. I always like to think, by the way, that Leibniz is just a more contrived and complicated version of the greater Spinoza. But okay, let's consider it as a joke. But you see what I mean, Gerardo. So this idea of you know, the pre-established harmony, that all info of the universe is everywhere in every point of view. Well, that seems to me like just a different way, you know, as saying everything is determined.
Yeah. What can I say? I am not sure.
Me neither.
Maybe. The thing is that, so for example, in pilot wave, you can imagine they would say that the complete description of the universe is given by a wave function and the configuration particles of everything in the universe, okay? And in that sense, that's the correct, how it evolves, it gives you everything that is to be known about the universe, okay? So it's completely deterministic. And that theory it's not super deterministic in the sense that it doesn't violate settings independence. So I think that somehow, somewhere,
which theory? Yours?
No, pilot wave. Standard pilot wave
violates setting independence.
Pilot wave doesn't violate settings independence.
No, you say that in your own paper.
No. Our version of pilot wave theory violates settings independence. Ordinary pilot wave theory doesn't violate settings independence. It's easy to see. Look, let's go to the experiment. Okay, so according to pilot wave theory, when you have an Bell-type experiment, you create let's say, Alice, I will use language of quantum mechanics because this applies in the case of pilot wave, but do not get confused. The theorem is not about quantum mechanics, but let's see how according to the theorem, things would run if you take something like pilot wave theory seriously. The idea is, in the source, a system is created, and according to pilot wave theory, the system is completely described by the wave function of the system, which is a singlet. We know that state, we can write it, we know all the properties that it's of that system according to quantum mechanics. And according to pilot wave theory, in addition to the wave function, you have the position of the particles that Alice and Bob will measure at the start, okay? And then you send the two particles, one towards Alice, one towards Bob, okay? And so lambda, what is lambda in this case? Lambda is the singlet and the configuration of the particles. And then the question is according to pilot wave theory, the setting that Alice will use, is it correlated with the lambda that the theory describes? Well, no. The setting that Alice used, for example, if she used information that comes from a photon, from a quasar, very distant quasar, this information is relevant for the fact that this lambda was a singlet, and that singlet involved two particles in some position. Okay, and this quantum mechanics also doesn't violate settings independence. In quantum mechanics, instead of the you only have, instead of the wave function and the configuration of particles, you only have the wave function. You have a singlet, okay? And how you choose the settings of Alice? Well, you have to look at some particular experiment. Let's say that Alice uses the digits of pi. Okay, according to quantum mechanics, if Alice uses the millionth decimal place of pi to choose what setting to use, that doesn't change the fact that she is measuring a singlet. So they do not violate settings independence.
I think we might discuss another time. I think I disagree, because you know, one can say that the singlet wave function collapses if you measure, and in this sense, I would say that, you know, it is correlated with A, not as the angle. I mean,
okay, let me.
But
we
okay,
should probably think about this. We should probably think more about this. It's really nice that you brought this point, because it is my strong suspicion that many of our disagreements have to do with this, okay? Because no. I think so. I think so. As I said, we had this disagreement about what lambda is, and I think that it might be related to this. I think that if you understand lambda, follow carefully, I think that you would see what I'm telling, that pilot wave doesn't violate settings independence, that you will have, and the same happens with
I see I see your argument. I see your point, but I don't think it is much related to the rest of the discussion. So, you know.
Okay. Okay. The connection is with when it came to your distinction between the lambda star and lambda the same, and I was saying that the lambda in Bell's theorem, it's the fundamental description according to some theory. So you take a model and you ask, well, we can imagine that quantum mechanics is just an effective description of what is happening. So if you think that, well, they'll do whatever. It's not relevant. But if you think that quantum mechanics is complete, that is, if you think that it represents everything that is there is to be known about the experiment you're performing, well, then you are saying that the wave function is fundamental, and that's the complete story of what it gives you, the complete story of what will happen with the experiment with Alice and Bob. Okay, and that to me is and I think that for Bell, that's lambda. Okay, so that's how I see the connection.
But is the consequence then that this lambda is correlated with A and B?
This lambda, well, in the case of quantum mechanics, the experiment of Alice is quantum mechanics gives you a conditional probability for the result of Alice, conditional on the singlet and the setting that she will use. Okay. Mm-hmm. So for the properties of the singlet, for any angle she uses, she will have 1/2 the probability of finding the particle up or down. Okay. So that is what the description of quantum mechanics. Yes, I don't know if I answered.
Yeah, sure. Yes.
I have seen some people. Okay, perhaps I have a lot of things to say, but perhaps in another time we can continue.
Maybe there are some people with other questions.
Yeah, Vladislav wrote 2 questions in the chat. If you could.
Oh, I will stop sharing.
Thank you very much.
You describe a model for solving Bell's inequalities. Do you think it will also successfully solve Leggett-Garrick's inequalities? Do you think the model should explain the quantum? I have not thought about these things. So my guess is that you would have the same explanation for quantum eraser experiments and delayed choice experiments as you have in pilot wave theory. So something akin to that. Yes. So sorry, I have not thought carefully about these topics.
But I think there is some difference, I suppose. Okay.
Yeah, there might be. Well, the explanation will be a little bit. It will be similar to pilot wave, but you will have to disclose a lot of stuff. You know, like, yeah, so what is happening? There is no causation. In reality, you have this pre-established harmony, and I'm just telling you these properties of this pre-established harmony. I'm not telling you anything dynamically that happens between the points. Something like that would happen.
Okay, thank you.
Do we have any other questions?
I have one more. Why do you say that your theory needs an absolute rest frame?
Because it is defined for points in space. Okay, so the idea is that for each point in space, you assign these internal degrees of freedom, and by construction, you are postulating that there are these physical points that they continue through time. So it is very similar to the absolute space that you have with Newton.
And Newton returns. Yeah.
In any case, Bohmian theory has a big problem with relativity theory.
Yes, yeah, and our model is even worse. In Bohmian mechanics, you need to have a preferred foliation of space-time. Okay, in our model, that is even worse because it is not only a foliation. You have this fixed sense in which you have like the world is a slide in pieces of time, and you have these points that continue through time. Yeah, so it is even worse in our model. But yes, pilot wave also has it's difficult to find a relativistic solution, a relativistic version of pilot wave theory.
Yeah. Are there other questions? From anyone to anyone?
Yes, may I ask one more question?
Of course.
I'm physicist by my background, education, university education, but I forgot physics. I liked quantum mechanics. It was 40 years ago. I made not PhD, but thesis in one of the level of my education. I wrote a work about quantum mechanics. But now I would like to ask a question to Louis, maybe, because maybe to Gerardo as well, about the Leibniz idea of pre-established harmony. According to my view, I am dealing with a complex system, theory of complexity, and evolutionary view, pre-established. So my question is, are you sure that the Leibniz idea of pre-established harmony is still modern, is still valuable in the context of the modern scientific knowledge. Because in my view, to my opinion, which is evolutionary one, we have post-established harmony in the world, post-established, not pre-established. And if we talk about pre-established harmony, it seems to me that this pre-established harmony exists only in speculative world, like the world of ideas, eidoses, Plato world, speculative world. Is it possible to connect this idea? Sorry, not enough light here in my room. Is it possible to connect this idea with all load of scientific language today, all baggage of load, all the basis of scientific language connected with evolution, global evolution, Big Bang, biological evolution, human evolution, noosphere, and till the omega point, as by Pierre Teilhard de Chardin. Is it possible? For me, it's like a game. The pre-established harmony exists only in our brain, or in brain of super subject, a Devin subject, who knows all the information about all the particles in the world. How it's possible? How it's possible? It's like a Laplacian diamond.
Yes. Well, that's a very wide-ranging question, Elena, and it's very appropriate for the very late time of the evening. I wish we could sit, moreover, around the table and maybe drink something to go much deeper into this. But very quickly, what do you mean with post-established harmony? That we can see it only?
We can see it as observer, We can see this order out of cases, structures, complex structures of the world. This is a post-established harmony.
Well,
when we take into account the anthropic principle, cosmological anthropic principles in strong sense of it, then we can maybe we can say that there is this pre-established harmony.
Elena, Louis, I think you are both right. Leibniz says about pre-established harmony in potentiality, and you say about post-established harmony in actuality.
In real world.
Yeah,
in real
there is
nature,
no contradiction.
In real nature, in physical nature, in biological nature, human world, there is no pre-established harmony. We are
in potential.
But this is only one possibility.
Well,
one possibility of a whole multitude of different possibilities.
Well, you're right that this pre-established harmony is certainly not a modern idea, but some philosophers, they like to revive ancient ideas, and I happen to be one of those. So for me, this pre-established harmony, yes, if you equate it with the determination of what happens in the universe, reduced to a limited set of laws. For me, this pre-established harmony has an appeal, and I hope to show that it also has an explanatory function. But one other way to respond to you, Elena, is to say that, you know, when you look at this, for instance, this order which emerges from a chaotic deterministic universe, which we can see as observers and which is actualized, well, you know, there are very good theories which explain it from simple laws. And therefore, I would see there the pre-established harmony, which resides in these deterministic models, which, you know, yes, of course, they are not fully deterministic, because you need, as also in the model of Gerardo, you need some randomness in the initial conditions. But that's a detail, you know. You could even attribute this random values in a deterministic way, but okay, that's not interesting now. I would say that, you know, good theories, they do coincide with what happens in the real world. It's our theories, and it's an epistemic way of getting to know things, but I think that good theories, they all lead to this idea of, if you like, pre-established harmony or determinism. But I'm not very modern here. I don't know. Did I give you a little glimpse of what I'm thinking about? Some people say that I'm a mysticist, but okay, that's fine.
Perhaps I can say something quickly. Okay, so we can never know what is the correct theory of the world. Okay, so it might be in the end that in reality there is something like pre-established harmony occurs, and that there are some systems that interact, perhaps particles in the universe, and actually they don't interact. They just act as if they interact, and they were just put forward by God, and he organized the movement of each one of them. Okay, that is basically the idea of the pre-established harmony, and it was made in the context of Leibniz trying to find a solution to the mind-body problem. The problem was the following: if the mind is different to the body, okay, these are two different substances, how can it be that they seem to interact with each other? How can a physical brain have an influence in this other substance that is not located in space-time? That seems odd, weird, fantastic. And his solution was that, well, in reality, there is no interaction. There is this pre-established harmony, okay? And I would say that this idea was quickly abandoned. I think there is a quote by Kant, which he said that, well, this is the alternative you take once you have abandoned all hope for a good explanation of the body-mind problem. But let's leave it like that. And I would say that, yes, it is a basic idea in how we conduct physics today. And it has been like that for many, many years. The idea that you explain systems by the interaction between the different parts in the system that are located in space-time, okay? That doesn't mean that you can eventually find some analogous description of the same thing in which you have a pre-established harmony. And, our model is an example of doing something like that.
Maybe we can end with this nice summary of Gerardo's theory, put in a wider context by Elena. Or Elena, you want still to comment on it?
No, it's enough. That's it. Thank you.
Thank you for all the questions, Elena. Thank you, all of you.
Thank you a lot, Gerardo. Let's continue, hopefully, the discussion at some point.
Yes, at some point we will continue. Thank you very much, Louis. Thank you, Anastasia.
Thank you.
Thank you very much for participating.
And good luck, everybody.
Good luck.